Controlled Environment Plant Production Engineering Technology education modules are developed and presented in collaboration by The Ohio State University, Rutgers University, and the University of Arizona, with support from USDA, NEFA, through their Higher Education Challenge Grant program. In this module, we will discuss topics related to humidity management. The first module will talk about the key parameters describing greenhouse humidity environment. This module is presented by Dr. Peter Ling, who's an associate professor of the Ohio State University. By the end of this module, you will be able to first define relative humidity dew point and vapor pressure deficit, and second, describe the effective use of the tools for quantifying humidity. First, look at the definitions of the few terminologies. Relative humidity is the amount of water in the air compared to the total amount of water the air can hold. Temperature affects air's water holding capacity, that's relative humidity. For example, if the air has a relative humidity of 80% at 20 degrees C, when the air is warmed up to 26 degrees C, then the relative humidity will drop down to 56%. This is because warm air has a greater capacity for water vapor. When the same air is cooled, then the relative humidity will increase. The same air we discussed earlier that has 80% relative humidity at 20 degrees C, when it is cooled down to 16 degrees C, the relative humidity will increase to 100%. And this temperature, which the relative humidity reaches 100%, is known as the dew point. Dew point is a very important concept in plant production, because if a surface in contact with the air at the dew point or below, condensation will occur on that surface. This surface could be the surface of a superstructure overhead, or it could be the canopy leaf surface. As long as the surface temperature is at dew point or below dew point, condensation will occur. Will condensation form in a room of 20 degrees C and a 40% relative humidity? Some of you may say yes, some of you may say no. When we first look at this, it seems to be a very dry environment with only 40% relative humidity. But in some conditions, condensate may still form. For example, if we are pouring a soft drink into a glass filled with ice, after a few minutes, we can observe condensate form outside of the glass. This is because the dew point of the air at 20 degrees C and 40% relative humidity is 6 degrees C. If a surface temperature is below 6 degrees C, then condensates will form. And because of the ice inside, the surface of the glass is below 6 degrees C. That's where the condensate form. So don't be fooled by the dry and warm outside condition and assume there's no condensate will form. This is the same situation in greenhouses. We discussed relative humidity in the previous few slides, but the relative humidity information alone does not tell us how easily plants can transpire or how narrow a margin for condensation to occur. And this is very important for a greenhouse manager to decide when dehumidification is needed for humidity control purpose. There is another measure directly related to transpiration rate and the condensation risk. Here we are introducing a new terminology, which is vapor pressure deficit, or VPD. Vapor pressure deficit is a difference of water vapor pressure between the amount of moisture in the air and how much moisture the air can hold when it is saturated. VPD combines two environmental parameters that are relative humidity and temperature information, and can be used as a simple indicator of plant transpiration potential. In this slide, on the left-hand side, shows that energy balance of a leaf. The primary energy source of the leaf is from radiation load from the sun shining on the leaf. And the heat losses, including radiative heat loss, including the convective heat loss, and also the energy loss due to the phase change of the water from the liquid phase to gaseous phase. And this is the process of transpiration. And on the right hand side, we see that mechanism of the photosynthesis. CO2 coming through the stomatal opening, and we see the water vapor going out through the stomatal opening. And the gas exchange rate here is affected by amount of water vapor, or the suction force in the air. Just like a vacuum machine, when we have a strong vacuum machine, creates a large vacuum force, and that makes the water leaving stomate easier. And that's a condition of a high vapor pressure deficit. But when the outside condition is cloudy and temperature is low, then the vapor pressure deficit is low, then it's more difficult for water to leave a stomate. VPD in the context of plant production can be thought of as the difference between the amount of moisture in the air and how much moisture on leaf surface. The greater this difference, the greater the driving force of transpiration. On the right hand side of the slide, we see two leaves in two different environments. One has a lot of dry air surrounding the leaf, and it's a lot easier for the water molecule to leave from the leaf surface to the air. And this is under high vapor pressure deficit environment, because a few water molecule is in the air. At the bottom right, we see a lot of water molecule in the air, and that reduces the suction force for moving water molecule on a leaf to the air, and this is under low VPD environment. Next slide, we're going to talk about different measurement devices for relative humidity. Wet bulb, dry bulb psychrometer is commonly used for relative humidity measurement. There are motorized versions, but here we are showing a sling psychrometer that is equipped with a dry bulb temperature thermometer and a wet bulb temperature thermometer. By acquiring the temperatures of the dry bulb and wet bulb, then the relative humidity can be determined using psychrometric charts. There are also hygrometers that can be used to measure the relative humidity. There are indicators, analog indicators, and also digital display. Then there are also hygrometers with electrical outputs that can be connected to a data logger or a computer for data logging purpose. For the next few slides, I'm going to demonstrate how VPD can be determined. This is very similar to using psychrometric chart to determine relative humidity or dew point. In this chart, on the y-axis, we see the vapor pressure data, and at the x-axis, we see the temperature. And you can find this chart following this link. http://ohioline.osu.edu/ax-fact/0804.html. Okay, let's look at this example. We want to find the VPD of the air at 10 degrees C and 80% relative humidity. First step we do is to find the temperature on this chart, which is 10 degrees C. It's 10 degrees C here. Then we go up to the straight up to the relative humidity of 80%. The next step is to go across, draw a horizontal line from this 80% relative humidity all the way to the right. And that gives us a vapor pressure of 1 kilopascal. Next step is that we want to find the vapor pressure at 100% relative humidity. Then we do the same thing as before. We draw a horizontal line to the right. Then we can get a vapor pressure reading of 1.22 kilopascal. Now the difference between these two vapor pressures is 0.22 kilopascal, and this is the vapor pressure deficit. That is how much more water vapor the air can hold before it saturates. Now we're going to do another example, which is try to find VPD of the air at 21 degrees C and 80% relative humidity. Similarly to what we did before, first we find the temperature, which is 21 degrees C, and we have a blue dot showing on the 21 degrees C. Then we draw a straight line up to the relative humidity, which is 80% of relative humidity. Here we look at the 80%. This is 80% relative humidity, and we have a curved line come down here, and that is where the temperature of 21 degrees C and 80% relative humidity at this point. Then we draw a horizontal line across to the right, here. Then we can determine the vapor pressure is 2.00 kilopascal. Next step is to find the vapor pressure of the same temperature but at 100% relative humidity. Same thing, we draw a horizontal line to the right, and we find the vapor pressure is 2.50 kilopascal. So the difference of the two vapor pressures, or the vapor pressure deficit, is the difference of the two readings, which is 0.50 kilopascal. The two examples above, assuming the leaf temperature is the same temperature as air temperature. For most applications, that is a reasonable assumption that gives you reasonable accuracy. However, in situations when a plant actively transpiring or plants are under stress, then the leaf temperature will be different from the air temperature. In this case, for more accurate determination of vapor pressure deficit, then we need to use leaf temperature as a temperature rather than totally rely on the air temperature alone. Here's the example of finding vapor pressure deficit of the air of 80% relative humidity and 21 degrees C, but in this case, leaf temperature is 24 degrees C. When the leaf temperature is warmer than the air temperature, it's indication that plant is under drought stress because it cannot transpire enough water to cool itself. Then the temperature of the leaf will rise. So in this case, we first will find the air temperature, which is 21 degrees C. Then we go up to the air relative humidity, which is 80%. Then we go across horizontally to find the vapor pressure. That gives 2.00 kilopascal. The next step is a little different from previously. Instead of go up to the 100% relative humidity at the sampling temperature, we need to use an actual leaf temperature to find the vapor pressure. In this case, leaf temperature is 24 degrees C. As indicated here in the blue dot at the bottom. Then we go up to 100% relative humidity. This is because we can assume leaf surface moisture level is 100%. Then next step is we go across horizontally to the right. Then we'll find the vapor pressure, which is 3.00 kilopascal. Now the difference between the two vapor pressures is 1.00 kilopascal. So from this graph, we can tell that a larger vapor pressure deficit exists when leaf temperature is warmer than air temperature. And that means plants need to transpire more water to cool itself, and that is indicated by the larger vapor pressure deficit and the more driving force to move water. But if the plant does not have enough water, then the plant is experiencing drought stress. These are the three examples we're going to share with you today. Just be sure that you can go to that website here, the link here, to get the graph for you to determine vapor pressure deficit. Go to this link. This is a Ohio line link. Then you can find this graph. And when you know the temperature and you know the relative humidity, then you can use the chart to determine the vapor pressure deficit. Let's review what we have learned about VPD. First question is, at a constant moisture level, when temperature rises, does VPD decrease or increase? At a constant moisture level, when temperature rises, air's water holding capacity increases, and that presents a larger vacuum force to help water molecules to move from the leaves to the air. Thus, VPD increases. Next question, when a plant experiences drought stress, the leaf temperature goes down or goes up? When a leaf is experiencing drought stress, that means it does not have enough transpiration. And when plants do not have enough transpiration, then it cannot dissipate heat, and the leaf temperature goes up. The next question, when plant experiences drought stress, the leaf VPD goes down or goes up? When plant is experiencing drought stress, it means it's not getting enough water to meet the demand. Therefore, the leaf VPD will go up because that's a larger driving force to encourage water to leave leaves. But since it does not get enough water, then that causes drought stress. Last question, at a given temperature, when relative humidity increases, does VPD decrease or increase? When relative humidity increases, does VPD decrease or increase? Relative humidity and VPD, they go in opposite directions. When relative humidity is higher, then vapor pressure deficit decreases. When relative humidity is high, it's more difficult to water molecule to go from leaves to the air. That's VPD goes down. We'd like to acknowledge the funding source of this project. Thank you for watching and hope to see you again soon.